Hello everyone, welcome to section 6.1. In this section we're going to talk about set theory. We've talked a little bit about sets already, but we haven't really dug deep into what we can do with sets as far as comparing them. Are these completely different sets? Do they have some overlap in terms of their elements? Is one set completely inside of another set? And that's what we want to define in this section. So we're going to need to start with a bunch of definitions. We'll get through some definitions, and then of course I'll give you some problems, some examples to work through. So let's start by defining what we call a subset. So first, I'm going to say let A and B be sets. I'll use capital A and capital B, and I'm going to stick with this throughout the entire lecture here. This will all, anytime you see the capital A or the capital B, this will all mean set A, set B, and they're just generic sets. I might, in examples, I might define them a little better with their elements, but for now we just want to talk about generic sets to get through the definitions. So we say that A is a subset of B if for every element X in A, if X is in A, then X is in B. So if we look at any element in A, if it's also in B, then we would say that A is a subset of B. Our notation for that looks like this. A is a subset of B. Visually, what that looks like is, and I'm just drawing a generic example here, is that here's set A, here's set B. Every element X that I can find in A, I can also find in B, because guess what? There they are. Every element in A is also contained within B. Right? And there might be some more elements in B, but I was mainly concerned about the set A first. So again, we could call this the subset A. We can negate this statement. Right? We say that A is not a subset of B if there exists at least one element X, we'll just call it X, in set A, well, let's say X in A, that is not an element of B. All right, so X is in A, but it is not in B. Again, here's the notation. Of course, we do what we normally do. We just kind of put the slash through it. A is not a subset of B. And visually, what that looks like is, well, here's our set A. It's got a bunch of elements. And then here's our set B. Yeah, some of them are also contained in B, but this one, this one, this one, those are not contained in B. They're separate. So I can't just look at set B and find everything that's in A. I have to leave set B in order to pick up the rest of A. So A is not a subset of B. Now, the next thing we can talk about is what we call a proper subset. So our next definition, again, letting capital A and capital B be generic sets, we say A is a proper subset of B we've got two criteria that we need to meet. And those two criteria are number one, well, first of all, A has to be a subset of B. Right? If A isn't a subset of B, then there's no way it can be a proper subset. So we need to look at those first and say, is A even a subset of B? If it is, then we can move forward. The second criteria is that there is at least one element in B that is not an element of A. And again, to draw you the picture where A is a proper subset of B, here is A, it has a bunch of elements inside of it, here is B. There is at least one element in B that is not in A. That means this is a proper subset. It is fully contained by B, and B has extra stuff. That's what these two stipulations mean. First one meaning A is completely contained within B, and it's not the exact same thing as B. B has something unique as far as elements are concerned. There's a unique element in B that is not also in A. So they are different sets. That's when we say that A is a proper subset of B. And then one more definition that we can talk about is, well, what happens when the thing you just said is the thing you just said? If A and B are the same set, that means we have equality of sets. All right, so we say two sets, A and B are equal, written A equals B, right, as we normally would write it, right? A is equal to B. If A is a subset of B and B is a subset of A, if we can show that the set A is contained by the set B and the set B is also contained by the set A, then they must be the same. That is, sorry, this is a little confusing here. Right? This is set A. This is set B. I'm going to destroy my green marker, but it'll get the point across, and that's all that matters. Sorry, green marker. They're the same set. They have the same elements. Everything that's in B is in A, and everything that's in A is in B, and vice versa. So we would say that these two sets are equal. We would use this notation, A is equal to B, when both of these happen. If we're in a situation where A is completely engulfed by B, but B has some extra stuff, and they're not the same set, we lose that equality. So that's why we show it in both directions. Right? As a silly example, we would say that 2 is equal to 2 by showing that 2 is less than or equal to 2 and 2 is greater than or equal to 2. We lose the strictly less than, we lose the strictly greater than. It can't be both greater than or less than, it's got to be one or the other. And if both of these are met, then we have our equality. And so if both of these situations are met, then we finally get our equality. So that's what we do with sets. We compare their elements and see what happens. Now, as an example, if we look at let's say we look at the set of integers. Right, we use this notation, this fancy Z notation. This script Z represents the set of integers, all the positive and negative whole numbers and 0. That is a subset of the real numbers. Right, the real numbers have all the integers, all your fractions, irrational numbers, pi, e. Right? So the integers are just a smaller subset of the real numbers. In fact, the integers are a proper subset of the real numbers. Again, the integers are just positive and negative, 1, 2, 3, 4, 5, etc., and zeros in there. Whereas the real numbers have way more elements that Z does not have. So Z is comprised of all the elements of R, but R has extra stuff. That makes Z a proper subset. The real numbers are not a subset of the integers, right? The real numbers have extra stuff like fractions. And this doesn't have fractions, right? So this, the set of real numbers is not a subset of the set of integers, which means, of course, it fails the criteria for our definition. The real numbers are definitely not a proper subset of the set of integers because it's not even a subset to begin with. So we'll work with more finite sets. You know, these sets are actually infinite. The integers never stop. The real numbers never stop. The examples that we'll work with will be more finite sets. So you've been seeing me draw these like circles to sort of represent sets, subsets, and you know, what are these circles? These circles are what we refer to as Venn diagrams. And these Venn diagrams help us visualize what we're talking about. So these Venn diagrams, when we write these diagrams out, we usually like to pick on a universal set and then we can draw our sets inside. Maybe this is set A and this is set B. But the universal set just kind of gives us a region to play within. Imagine like the universal set is the set of integers. And our two sets A and B, A could be the even integers, B could be the odd integers. Well, then there'd be no overlap. They would be completely separate. Right? So we can draw these Venn diagrams in different ways to sort of visualize the things that we're talking about. This could be A, and this could be B. You could have a Venn diagram where if A is a subset of B and B is a subset of A, guess what? A equals B. They're the same set. So these Venn diagrams help us visualize which situation we're dealing with. So we can use these to kind of work through problems and figure out, you know, which sets are completely separate, which of them are the same. Maybe they only have some elements that are in common. So you'll see me draw these Venn diagrams to illustrate the next couple of definitions that we come across. So we've got a few more, I think four definitions more that I want to state. And then we'll get our hands on a nice finite example. So again, for these definitions, I'm just going to say let A and B be sets. And U will be the universal set that we use to kind of contain sets A and B. Now, there are infinite sets out there, so, you know, we are in this section mostly dealing with finite sets, but there are universal sets out there that we can talk about, such as the real numbers, the integers. So keep that in mind. When I draw the universal set, I'm not drawing it as though it has to be a finite set. The universal set could be the set of real numbers. It could be an infinite set, but I have to draw it so I can see it. So first thing that we want to talk about is the union of two sets. So again, let A and B be sets, and U the universal set. And I'll try and I'll keep these numbered for you because I'm going to roll through four definitions here. The first one is the union of sets A and B, written A union B, is the set of all the elements, or I'll say of all elements that are in at least one of A or B. Visually, what that looks like is here's a universal set, here's a set A, here's a set B. when I look at their union, maybe we'll bring some color in here. I'm looking at taking the set of elements that are in at least one of these sets. It could be in the overlap, it could be in both sets, that's fine, because then it is in at least one of the other. So this is what the union of A and B looks like. It's just all the elements that are in A and also in B. So maybe to really emphasize it and drive the point home, it's just everything in there. Number 2, the intersection of sets A and B, written A intersect B, is the set of all elements that are in both A and B. It has to be an element that is in both of those sets. It can't be exclusive to one set or the other. So again, here's our universal set. Here's our set A. Here's our set B. If we're looking for their intersection, right, then we want, think about the intersection when you're driving your car, you come to an intersection, that's where the traffic crosses. Same thing here. It's where the traffic crosses. It's the elements that are in both the set A and the set B. So we want to pick those up. And we've seen this notation before in college algebra when we talked about, the real number line. We talked about less than or equal to, greater than, equal to, all that fun stuff. We looked at unions. We looked at intersections, especially when we talked about, the domains of functions, and we use that interval notation. Again, we use that union. We use that intersection. So that's the notation for the union. It looks like a cup. And then this looks like a cap for the intersection. So there's the first two, and then I'll leave that first line up there because we want the same A and B to be general sets and U to be our universal set. But now we'll talk about the difference of two sets. When you see difference, you think subtraction. It's not exactly subtraction, right? Sets are more general. You could talk about the set of colors. What's blue minus red? That doesn't really make any sense. So when I say the word difference, I'm talking about not the subtraction of numbers that we're used to, but the difference of two sets. The difference of sets A and B written, but we do steal the notation A minus B is the set of all, I capitalize that, all elements that are in B but not in A. So again, what that looks like is universal sets. Here's maybe a set A, here's maybe a set B. All the elements that are in B but are not in A, meaning I'm not allowed to use that intersection. I just want all the elements that are in B but not A. So that looks like this region right here. Again, this being set B. All right, so I can't use all of B if there's some overlap. Now, if these two sets are completely separate, then of course I would take all of B, because all the elements of B would completely be separate from the elements of A. But if there is some overlap, then I just get rid of the elements that A and B share. So that is the difference of sets A and B. Right, and we write that out as A minus B. Oh, sorry, I have it. Adjust the definition. Adjust the definition. Right. I did A minus B up here, I meant B minus A. Right, so the difference of sets, we're taking the set B and we're subtracting A. It's all the elements that are in B but not in A. My apologies for that extremely here. Written B minus A. I just had those swapped in the definition. We're taking all of set B but removing the stuff that it shares with A. So we lose that stuff. Excuse me about that. Sorry about that. B minus A, not A minus B. And then the fourth thing that we want to talk about, and this will be the last one, last definition. Well, there'll be another definition, but I mean, for now, before we get to a nice example, will be the complement. The complement of sets A. Well, actually, here we go. I just need set A. The complement of set A is the set of all elements that are not in A. Set of all elements, I'll say in U, the letter U, that are not in A. Again, visually, what does that look like? Here is the set A. There could be another set B, but we're talking about the complement of set A. Ooh, and I should say written A, looks like A to the power C. Right, that's our notation. So when we want to find the complement of A, let me pick on a different color, purple here. Then we want all the elements that are not in A. Right, careful, there's some overlap here, but those elements are also in A, so I don't want those. Right, so anything in my universal set, as long as that doesn't dig into A. Right, so it's all those other elements. Basically what it's doing is it's leaving us this set A taken away from all the elements of the universe. So that is the complement of A. And again, the notation, just because I didn't put it in there exactly, that looks like A complement. It looks like A to the C power, or at least I'm sticking with the notation the book uses for consistency. Okay, let's take a look at an example. We've got a lot of definitions. Let's get a problem out of the way. Let's see how we can use this. I'm going to say, let U, the universal set, be the set A, B, C, D, E, F. A be the set A, C, E. And B be the set, let's pick on D, E, and F, the last three. Let's go ahead and find A intersect B, A union B. Let's go ahead and find B minus A, and then while we're at it, we'll find A complement. All right, so let's go through one of the definitions each here. I think I swapped it. I think I did the union definition first and then the intersection definition. But let's find all four of these. Doesn't matter really what order we do them in. So when we look at this and we want to find these intersections and unions and difference and complements, let's go ahead and first start by using a picture to guide us through our solution here. So here is the universal set. Here is the set A, and here is the set B. And again, this is why we try to stick to capital letters for the sets and lowercase letters for the elements. So now when I look at set A and set B. Notice one thing right off the bat is that both of these sets share the element E. That means that E must be living right here, somewhere in between. It has to be in both A and B. I can't write E over here because then it won't be in B, but it is in B. And I can't write E over here in B because then it won't be in A, but it is in A by definition. So I want to make sure I put E in the right spot. A contains A and C as well, so it has E in it, but it also contains A and C. So I'm just going to put a little A and I'll put a little C. And so now I can keep track of those elements. Now when I look at set capital B here, it's also got D and F in it, so it does have a D and it has an F element. All right, but notice I write that strictly in B because I don't want to put it in the intersection. I don't want to put it in the overlap because that would be me forcing D and F into A as well, and it's just not in A by definition. Okay, so now let's look at what's left over. We had elements A, it's in the right spot. B, we don't even have B. Lowercase b is not in A, and it's not in capital B, which means it must be living somewhere out here in the universe. We've got C, we've got D, we've got E, and we've got F. So now we've put everything in their proper locations, which means now that when we look at this, it's a little easier to digest what these intersections and unions and difference and complements all are. So let's go for that. Let's say first we'll find A intersect B. Now the intersection of two sets is also a set, so we're going to use the set notation. The intersection is the element E, and that's it. A union B, we want the elements that are both in A and B. We'll just take them all and collect them. A, C, E, D, F, yeah. So A is in there, C is in there. I'm just going to keep it in alphabetical order here. A, C, D, and then E, and then F. Then we want to look for B minus A, the difference of B and A. Again, the difference of two sets, also a set. So what that means is I have the set B, but I get rid of all the elements that are also in A. That's E, goes in the trash. So it's just D and F. I take every element of B, and then I get rid of the overlap. I get rid of the stuff that's also in A, goodbye stuff in A, which loses E. And then the last thing I want to look at is A complement. When I look at the complement of A, I want all the elements that are not in A. Sorry, lowercase a, sorry, lowercase c, sorry, lowercase e. That is B, D, and F. Right? Notice it picks up the B, which is out in the universal set, because B is not an element of A, and that's all A complement is. It's all the stuff that's not in A. Right, so that's using a Venn diagram to wrap our head around a nice finite example. Now again, these sets can be infinite, and they can be infinite sets. But when we deal with problem solving in this section, obviously we're going to be sticking to nice finite sets so that we can actually write these sets out nicely. Okay, almost there. Another definition, and then just one more after this. So two more definitions. We want to say that two sets, A and B, are disjoint if A and B share no common element. Or I guess you could say elements. Right, but really they don't have anything in common. what that looks like is, and I've already showed a picture like that. Here's set A and here's set B. Oops, let me draw a circle and put the B there so that they're completely separate. They do not have any overlap. They do not share any elements in common. One notation for that, a way of expressing it, is that A intersect B is the empty set. So this notation right here, it's not a zero. This is what we call the empty set. Right? This empty set notation can also be written out as basically saying it's a set with nothing in it. Right? Don't put zero in there because zero is something, and then it's not empty. We just use the curly braces that say, here's a set that contains, it has no elements. It contains nothing. Right, so a good example of two sets being disjoint would be, the set of all even integers and the set of all odd integers. Those are completely disjoint sets. There is no integer that is both even and odd, so their intersection is empty. Right? 0 is even, 1 is odd, -1 is odd. Right? So don't even try and mess with 0 and try and play that game. 0 is an even number. Okay, and then finally, and we're at the home stretch now, one last definition, and that is the power set. The power set of A, written P of A. Our book uses a much fancier version of P. I can try and sort of emulate it. It's got this little curl thing here and looks like that. Ooh, super fancy. And don't mind if I use the regular P, please. We write it out as P of A. And that power set P of A is the set of all possible subsets of A. And I think this one's good to just kind of lead with an example. Let me show you what I'm talking about. Let's say that A is the set containing the elements 1, 2, and 3. Find the power set of A. So it is all the different subsets that we can construct from this set A. So when we look at set A, it has 3 elements. How many different ways can I construct subsets? Well, I can have a subset containing the element 1, I can have a subset containing just the element 3, a subset containing both elements 3 and 1, right, et cetera, et cetera. So we need to look at all those combinations. So again, I'm just going to stick to P of A is going to be the set. Well, the first subset that I can create is the empty set. The empty set is always a subset of every set. Right? Even the empty set itself has a subset, the empty set. Right? So that's the first thing that I can do. I can create the empty set by just choosing not to take any elements. There's a subset. Right? A set with no elements is a subset of a set. Then I can pick on, okay, what about the set containing 1? That's a subset. I can use this as a subset. What if I just pick up the element 1? Now, I don't want to write just the number 1, right? I want to find the sets, all the subsets, the set that contains all the different possible subsets. So that's why I'm using the curly braces again for the set notation. I could take just the element 2. I could take just the element 3. I could take the element 1 and 2 and put those in a subset that has 2 elements. Or I can take 1 and 3. Or I could take 2 and 3. So now I've constructed all the different ways I can take just 1 element, all the different ways I can take 2 of the elements. I'd be repeating myself if I said 3 and 2. Right? Order doesn't matter. Right? This is the set that contains both those elements, the element 2 and the element 3. If I say element 3 and element 2, I'm just repeating myself, not generating a new subset or a unique subset. And then, of course, I missed the possibility of just taking all of them. Right? A is a subset of A because A equals A. Right? So I could always just take A itself and call that a subset. The subset of the set containing 1, 2, and 3 is the set containing 1, 2, and 3. So that works as well. Notice how many elements I have, and we'll go ahead and count them up. 1, 2, 3, 4, 5, 6, 7, 8. And notice how many elements that we had in the original set A. 1, 2, 3. Oh boy, I hope I'm not rocking anyone's world there by counting out 1, 2, and 3 as 1, 2, and 3. Look at the elements that we've gotten. We've gotten 8 elements, and these elements are sets themselves. If I look at the number of elements in A, I get 3 of them. I can quickly determine how many subsets I should be able to get. That is to say, I can determine the size of the power set of A. The number of elements in P of A is 2 to the 3, which is 8. See that? So this is actually very nice. It allows us to determine, hey, did I get them all? Did I get all the different subsets for the power set? It very quickly allows us to determine yes or no. So real quickly before we just wrap it up, I'm not going to go through the entire process of finding the power set, but if, let's say, let C equal the set A, B, C, well, just so it's not confusing that this is the set C. Let's do this. Let's do red, green, blue, purple, and yellow. All right, so this set contains some elements, and those elements happen to be colors in this case. Notice C has 1, 2, 3, 4, 5 elements. Thus, the power set of the set C has 2 to the 5 elements, which is 32. So if I asked you to list out all the possible different subsets, if I told you to give me a list of the power set of C, you need to find 32 different subsets. That takes a while. You can see how this ramps up very quickly. If I just put one more element in C, this is 2 to the 6th, which is 64 elements. Oh boy, I just doubled the amount of work, right? So obviously I'll keep the sets to a smaller size, maybe only 3 or 4 elements at most. But you can see that it could be a very lengthy process. But don't forget the empty set. It can always be a subset of any set. So if you find yourself coming up short and only finding 31 subsets, chances are you probably forgot the empty set. So shove that in there as well. So that is 6.1 in a nutshell. And we don't go any deeper into chapter 6. We just want to kind of touch on a little bit of set theory. And then, obviously look for the problems in the textbook, look at the problems in the study guide. The study guide's pretty short for this one. And again, I'm going to, keep the exam pretty short for this one because we just kind of do some stuff in chapter 5 and then barely touch on chapter 6. So I wanted to keep it a little shorter, a little more digestible. We're all still adapting to this new format, which again, I'm teaching to an empty room, which is not the most fun I've ever had. Trust me. I miss you guys. I hope you're happy. I hope you're healthy. Stay safe, and hopefully I see you sometime in the future soon. If not, just keep checking Canvas. I'll keep giving you some updates there. So thank you very much.